Hi everyone, this is Umakant. Welcome all of you to my YouTube channel. So this video is all about the important short tricks for the molecular spectroscopy. So in the previous video, I have mentioned the important short tricks for the atomic section of the atomic molecular physics, and this video will be about molecular spectroscopy. Okay. So basically, in molecular spectroscopy, we have three basic and important spectroscopy, that is rotational spectroscopy, vibration spectroscopy, and Raman spectroscopy. Okay. So I will discuss the most focused point of this spectroscopy. Okay. So in rotational spectroscopy, as you know, in rotational spectroscopy, this is due to, or this is all about the polar molecules. This is all about the polar molecules like HCl. Okay, so whose net dipole moment is not zero. So in this molecule, type of molecule, we get the rotational spectroscopy. So this concept is all about rigid rotor, that is two mass are there. So the rotational spectroscopy, in rotational spectroscopy, the rotational energy is coming like Ej equal to B into J plus 1. Okay, so a lot of question is framed from here. How? So let's see. This B is equal to rotational constant. This B is rotational constant, and its value is h cot square by 2I. So generally I is the momentum inertia. So it is h cot square by 2 ik plus mu r square. So here mu is the reduced mass, that is m1 into m2 by m1 plus m2. So here this m1 is the mass of this first body and m2 is the mass of the second body. So this is the reduced mass, and you have to substitute here. R is the bond length, this is R. Okay, so here taking all the factor into consideration, you have to calculate the required value that will asked in the examination. But the important thing is like that, in rotational spectroscopy, the energy that you get is equal to B into J plus 1. So you know this J can take the value like 0, 1, 2, etc. So the rotational energy level is discrete in nature. So this is a discrete energy levels. So you can have this energy level like that. So this is for J equal to 0. This is J equal to 1. So J equal to 2. This is J equal to 3. So if you calculate the energy difference between two energy level, conjugative energy level, that is daily equal to, that is daily. So it will be Ej plus 1 minus Ej. So it will be coming like 2V. So the separation between two conjugative energy level in the rotational energy spectra is 2B. This is important. Okay, and this is equally spaced energy level because distance is 2B. So this is equally spaced energy level. So this is an important point here. So next in the rotational spectroscopy, you know the say selection rule, that is a transition rule between two energy level, that is del J is equal to plus or minus 1. So you can have transition from the lower to higher or the higher to lower between two conjugative levels, not from like this to this. This is not a acceptable transition in the rotational spectroscopy. This is important. This is the selection rule for rotational spectroscopy, and this is happen microwave region. Microwave region. This is an important point. Rotational spectroscopy is always observed in microwave region, and this is all about the rotational spectroscopy. So let's move to the vibrational spectroscopy. So in vibrational spectroscopy, you generally assume the simple harmonic oscillation. Simple harmonic oscillation is taken. So its energy will be n plus 1 by 2 h cot omega. So the potential will be in the form of half ks square. So it is parabolic in nature. So here energy levels will corresponding to n equal to 0, that is ground state, for n equal to energy fast excited state, like this. So this is all about n equal to 0 state, this is n equal to 1 state, this is n equal to 2 state, and this is n equal to 3 state. So for n equal to 0, this energy level will be half h cot omega. This is the ground state energy level of a simple harmonic oscillator or quantum harmonic oscillator. So if you calculate the energy difference between two conjugative energy level, this will happen to coming to be h cot omega. Here it is also equally spaced energy level is there. But the question is coming like, so what about the selection rule in this vibrational spectroscopy? So the selection rule del n is equal to plus or minus 1. So here situation is also same. The transition can be expected from higher to lower or lower to higher between two conjugative energy levels. Okay, not from any other energy levels. Okay. So this is all about vibrational spectroscopy. Yes, also the question is coming from omega. Several times the people are asked questions from omega. That is, you mentioned En is equal to n plus 1 by 2 h cot omega. This omega is equal to k by m, that is reduced mass root over, and this k is spring constant. So this is spring constant. This mu is reduced mass. This omega is the angular frequency, and you can put is a 2 pi by t or equal to 2 pi into frequency is equal to k by reduced mass root over. So different kind of NAT question can be framed from this concept. So you should know the proper utilization of this formula in the examination. So this vibrational spectroscopy is also for a highly polar molecule. This is for highly polar molecule like similarly HCl, KCl, and this vibrational spectroscopy is occurring in the IR region. That's why it is also known as IR spectroscopy. Okay, vibrational spectroscopy is also known as IR spectroscopy because we get it in IR region. So these are the simple and important formulas that is used in vibrational spectroscopy. So if you move to the Raman spectroscopy, you know this Raman spectroscopy is very much important because it is used to know the molecular composition or the spectroscopy of a nonpolar and symmetric molecule, nonpolar and symmetric molecule like S2, Cl2, etc., whose net dipole moment is 0. So that's why Raman spectroscopy is required. So in Raman spectroscopy, you have the energy levels like this. Okay, and there are three transition can be occurs. This is like a transition, this is relay lines, and the transition can have like this is anti-stroke transition, and this is a stroke transition. This is anti-stroke, this is relay, and this is Stokes line. Okay, so the wavelength of this Stokes line is greater of the Stokes line is greater than incident radiation, and here relay lines the wavelength is the same from the scattering radiation and incident radiation, but in anti-Stokes line the wavelength of scattered radiation is less than the incident radiation. This is the important relationship, and the intensity of the Stokes line is greater than intensity of anti-Stokes line, and intensity of relay line is greater than the Stokes line. So this is an important relationship between the intensity of relay lines, Stokes lines, and anti-Stokes line. So this Raman spectroscopy can have two form like rotational Raman and vibrational Raman. So if you see, then in rotational Raman, you have the expression like mu is equal to, that is mu naught plus or minus b into 4j plus 6, and here the selection rule is del j equal to 0 plus or minus 2. Okay, so here I have to mention one thing. The important question is coming from this expression, that is suppose this is the Raman line, this is the Raman line, this is the fast Stokes line, and this is the fast anti-Stokes line, and this is the second Stokes line, this is second Stokes line, and this is the second anti-Stokes line. Okay, so if you have to you have asked to find the distance between this Raman line and fast Stokes line, then you have to put j equal to 0. So if you put j equal to 0 in this expression, so del mu will be 6b. So this distance is 6b. Similarly, this distance between Raman line and fast anti-Stokes line also 6b. So this distance will be 4b, this distance will be 4b. So similarly, if you move for the third anti-Stokes line and in between second anti-Stokes line and third anti-Stokes line, so this distance will be similarly 4b. So you can have a question like what is the distance between the fast Stokes line, and fast anti-Stokes line. So it will be fast Stokes line and fast anti-Stokes, it will be 12b because this is 6b and this is 6b. So total distance will be 12b. So a kind of question can be framed from this concept. So you have to know the proper expression and the utilization as well as then move to the vibrational Raman. If you move to the vibrational Raman, this is also have a vital role in examination. So this have a particular form, that is uh, omega n is equal to n plus 1 by 2 omega plus or minus n plus 1 by 2 whole square omega e xc. This is omega e. So from this expression, this term is from for the harmonic oscillator kind of oscillation, and this expression is due to anharmonicity. Okay, this is the perturbation to the system, and this is the originality, because no system is in pure harmonic in nature. No oscillation is purely harmonic, because certain there is certain uncertainty, because molecule is not like that you are providing certain frequency up to what range you have, but the molecule will obey the oscillation in like in Hooke's form, that is f equal to minus kx. This is not the reality. The molecular may the molecule may break, the bond may break, and they may free, because they have certain strength. Okay, so up to that they will continue their oscillation as a simple harmonic. After that there will be anharmonicity will be there, and this term due to anharmonicity. This xc is known as a anharmonicity constant. This is anharmonicity constant. Okay, so but the question will be like a from fundamental band. The question will be from fundamental band, overtone, overtone, and hot band. Okay, so the question will be from this expression. So if you see, then they may have a question like what is the omega e omega from fundamental band, fundamental band. So you know, for fundamental band the transition will be from n equal to 0 to n equal to 1. For first overtone, this is first overtone, the transition will be from n equal to 0 to n equal to 2. For second overtone, the transition will be from n equal to 0 to n equal to 3. So similarly for third transition, the third overtone, the transition will be n equal to 0 to n equal to 4. But for hot band, the transition will be from n equal to 1 to n equal to 2. Okay, if the question will be like find the omega e for the fundamental band, so first of all you put n equal to 0 in the previous expression. So here put n equal to 0 first in this expression, then put n equal to 1, then subtract this expression. Okay, put n equal to 0 in the expression, put n equal to 1 in the expression, then subtract, you will get the del omega e or dual omega or omega n. Okay, so this kind of question is previously asked in GATE exam, so you should practice such type of question. Then if you have time and you have patience, then you can cover Frank-Condon principle. Okay, that is vibronic transition. This is also important, but I think rotational spectroscopy, vibrational spectroscopy, and Raman, that is included both rotational and vibrational Raman, is very much crucial. So never miss this portion of molecular spectroscopy. You may have additionally, you can may get 3 to 4 additional mark if you cover this portion. Thank you so much. Thank you for watching my video. Thank you for showing a great interest on my channel. Thank you so much.